Next, let's discuss a reaction called the Aldol reaction, which takes place with some of similar intermediates that we've been seeing in the previous reactions. Specifically, we're going to look at the Aldol reaction of acetaldehyde, which is the simplest possible substrate on which this reaction can occur. If we take acetaldehyde in an aqueous environment and we treat it with a base, we're going to form an equilibrium with this product here, a beta-hydroxyaldehyde. Notice that our product has 4 carbons, which means that 2 equivalents of our acetaldehyde molecule have been coupled together. This is the reaction of a carbon nucleophile with a carbon electrophile, and the mechanism has been found to proceed as follows. First, in the presence of a base, we can form an enolate anion, which will serve as a nucleophile for this reaction. Under these conditions, we also have acetaldehyde, which can react as an electrophile. These two can react together like we saw in the ketones and aldehydes section. This will produce this alkoxide ion, which can pick up a proton from our solvent, leading to our final product, which we will call an aldol addition product. If you'll notice in the mechanism that we just drew, we showed all the arrows as equilibrium arrows. This process is fully at equilibrium and it is fairly easily reversible. The equilibrium behavior is a little bit different for aldehydes versus ketones, however. For example, both of them can form aldol products when treated in solution with a base, but while the aldehyde will favor the aldol addition product, the ketone will generally favor the reverse reaction, which is known as retroaldol. This fragments the molecule back into 2 equivalents of ketone. We'll see that we can actually exploit this reaction and that it's very common in a lot of biological systems. Before we move too much farther, I'd like to give you some tips for drawing the products of aldol reactions. We can use this tip to draw lots of products that we'll be seeing throughout the rest of this video. If we have an aldol reaction that's taking place between a ketone or aldehyde and potassium hydroxide or some other base in a protic solvent, the first step would be to align the alpha carbon with the carbonyl carbon. This will line the nucleophilic group up with the electrophilic group, and we can move on to the next step of drawing the product. Next, we can erase the carbonyl group and fill it back in with an alcohol and draw a new bond between the alpha carbon and the carbonyl carbon. This will give us the basic connectivity of the 2 products, which we can then tidy up to make sure that we don't have any unusually long bonds. Under similar conditions to the reaction we've just seen, we can also do a related reaction known as an Aldol condensation. Aldol condensations are good ways to make unsaturated systems from ketones and aldehydes. In the example we just saw, acetaldehyde can undergo an aldol addition with itself in the presence of a base. If we were to treat this addition product with sodium hydroxide or an acid and heat it gently, we would favor elimination of water to form a new alpha-beta unsaturated carbonyl compound. Just to reiterate, the first process is called addition. The second process to do this elimination is known as aldol condensation. Generally speaking, we can do this reaction in a single step. We could take acetaldehyde and treat it with a base and heat it gently to favor condensation, or we could treat it with an acid catalyst and gentle heat to favor condensation as well. This is much more practical, and aldol condensation is usually done in a single step rather than stopping and isolating the hydroxyketone product. In fact, in some cases, as we'll see later, the hydroxyketone is actually not able to be isolated on its own. Though also being in equilibrium, aldol condensation heavily favors the formation of the product. This is due to the fact that we're making a new highly conjugated system which stabilizes the product relative to the reactants. Let's shift gears a bit to talk about the mechanism of that condensation step. The elimination part of the aldol condensation proceeds with a mechanism that's known as E1CB. Due to the fact that we can't just kick out hydroxide, it's a bad leaving group, the mechanism of this elimination is slightly different from ones we've seen in the past. In this reaction, hydroxide first pulls off a proton to generate the conjugate base, which is an enolate ion, and it's this enolate ion that actually undergoes elimination to extrude hydroxide and form our new double bond. Here's some good mechanism practice. Try drawing the mechanism for the acid-catalyzed aldol mechanism. Be very careful to keep an eye on proton transfers, and remember our rule about acid-base compatibility here. Take a moment and do this, then we'll compare our answers in a bit. As we would predict for a reaction that's catalyzed by acids, this reaction starts by the carbonyl group picking up a proton. This generates this oxonium ion, which can then lose a proton to generate an enol. Since this is happening under acidic conditions, the enol is going to be the intermediate that reacts as the nucleophile for these processes. Now, an enol is not a very good nucleophile, which means that rather than reacting with a naked carbonyl group, we're going to need to react this nucleophile with a protonated carbonylous electrophile. This will happen as we saw back in the ketone and aldehyde chapter, like so. This regenerates the oxonium ion at the carbonyl group and forms our new carbon-carbon bond. A proton transfer can happen here. This is very likely to be intramolecular as it proceeds through a six-membered ring transition state to protonate that OH group, making it into a good leaving group. From here, we can lose a proton. The proton is probably pulled off by our solvent in this reaction, which would be water in this case, to form our conjugated product. Now, before we move on here, a word about stereochemistry. In acid-catalyzed and base-catalyzed aldol condensations, the most stable stereoisomer of the alkene is favored since all of these steps are at equilibrium. It is not possible in these cases to favor the formation of the less stable alkene stereoisomer. Let's do a little bit of practice in drawing the products of these reactions. Let's do a little practice at showing the products of these reactions. So I'm going to show you these three reactions here, which I'll proceed via aldol condensation rather than aldol addition. Go ahead and draw the product of each. Pause the video, come back when you're done to check your work. In the case of the first reaction, we would be joining these two rings together to form this unsaturated ketone. In the case of the second reaction, we would make this highly unsaturated derivative. And in the case of the third reaction, we would get this alkene here. So far, all the reactions that we've seen have taken place between two identical aldehydes or two identical ketones. But what happens if our reaction partners are not identical? In those cases, these are called crossed aldol reactions, so we need to have a discussion about how useful these reactions are. So a little bit of spoilers here. The crossed aldol reaction that I'm showing you between acetaldehyde and propionaldehyde is not going to be useful in the long run. The reason why is that the way we've set this reaction up can form two different enolates which can react with two different electrophiles. For example, we can have acetaldehyde converted into an enolate reacting with acetaldehyde as an electrophile, or propionaldehyde converted to an enolate reacting with propionaldehyde as an electrophile. We can also have two different crossed products depending on whether we get the acetaldehyde enolate or the propionaldehyde enolate. So if we look at all of these starting materials, we can put them together to show all four different products that we could possibly form out of this reaction. Now, due to the fact that this reaction is equilibrium controlled, we may get more of one than the other, but reactions which produce large and diverse product mixtures like this are not so useful. What we really need is a way to make this crossed aldol reaction happen selectively, where we can choose which compound forms the enol or enolate, reacts as the electrophile. So then, under what conditions are crossed aldol reactions useful? Well, the first condition is if we choose a reactive aldehyde as our electrophile that has no alpha protons. Two common examples of these types of electrophiles are formaldehyde, which you can see on top, and benzaldehyde, which you can see on the bottom. Neither of these aldehydes has alpha protons, which means neither can be converted into an enol or enolate, meaning that these will not compete for the formation of the nucleophile in this reaction. If we combine these with another compound, say an aldehyde or a ketone, these will undergo smooth aldol addition or condensation reactions to produce products. So practice your product here and try to fill in the product I do. Take a moment to do this, unpause the video when you're ready. For the first reaction, we'll form this methylene group by adding on just the single carbon bound to two hydrogens. In the case of benzaldehyde, we will get this extended conjugated system. This is one of those cases where it would be very hard to stop at the addition product due to the extended conjugation heavily favoring elimination. To reiterate, the way that this reaction works, the reason why these are good starting materials, is that our electrophile cannot form an enol or an enolate, and in addition, these are fairly good electrophiles. So even an enolate could act as an electrophile, a much better electrophile partner, so will heavily favor the formation of the product that we've shown. How about other conditions under which crossed aldol reactions are useful? Well, the other way that we can do this is with what's known as a directed aldol reaction. A directed aldol reaction hinges upon quantitative enolate formation with a strong base, followed by addition of an electrophile. Let's take this as a target. How would we make this via a crossed aldol reaction? Our first step here would be applying some retrosynthetic analysis. We can find the alpha-beta unsaturated carbonyl group and disconnect this as it shows us where the nucleophile and the electrophile were. So running this reaction backwards, this product would form if we had this enolate reacting with this aldehyde as an electrophile. The way we would do this forwards is we would take our carbonyl compound, our starting ketone, and we would add LDA. This quantitatively and irreversibly forms an enolate, which means that once we do this, there is no more ketone present in the reaction mixture to react as an electrophile. In a second step, we would add this electrophile, and we would do so very slowly. The reason we're adding it slowly is to favor the addition reaction while suppressing any formation of the aldehyde enolate. In the third step, since this is an aldol condensation reaction, we would add a proton and heat it in order to dehydrate, forming the double bond. Some notes on this process. First, again, highly conjugated systems will sometimes eliminate without any help. So in the case of this aldol condensation here, this reaction will proceed smoothly without ever stopping at the addition product, even at fairly low temperatures. Second, in the lab, the success of a directed aldol is contingent on the relative rates of proton transfer versus nucleophilic addition. What do I mean by this? Well, if we take these two materials here, we can imagine two different reactions happening. One, we could have nucleophilic addition to the carbonyl carbon to form the aldol product. But the other option is that these enolates are also fairly strong bases, so we could use this as a base to pull off the proton, forming the aldehyde enolate instead. The relative rates of these two processes is what determines whether or not we will be successfully able to do the directed aldol addition. For our purposes, we're going to assume the aldol reaction can be favored somehow by tweaking experimental conditions. This is an issue you would deal with in the lab. On paper, we will always assume these work. One of the best applications of aldol reactions is the intramolecular aldol to form a ring. These are extremely useful and also very common in biological systems. For example, if I have this ketoaldehyde here and I treat it with sodium hydroxide and heat, what are the products that I could possibly get out of this intramolecular aldol reaction, and which of the products is favored? This requires some fairly deep analysis, so take plenty of time to go through this. Start by figuring out how many products form, move on to drawing all those products, and then finally look at the reactions you set up and try to figure out which one of your products would form most favorably. Pause the video, take all the time you need, come back and we'll walk through it together. Alright, so where do we start here? I would say the best place to start is by locating all of the alpha carbons that could potentially act as nucleophiles. This compound has 3 potential alpha carbons which are all different, which means that we're likely to form 3 different products. After doing this, I'm going to draw the 3 possible enolates that I could get by deprotonating at each of the 3 alpha positions. By doing so, we can see the size and shape of the ring that's going to be formed when these things react internally. For example, in the case of the red molecule on top, if we number the carbons from nucleophile to electrophile, we'll see that we're going to get a 4-membered ring. In the case of the blue molecule, we are again going to get a 4-membered ring, but this one will be different from the first one that we drew. In the case of the third product, we're going to end up forming a 6-membered ring. So these are the 3 products that are possible if we try to do this intramolecular reaction. But which one will be favored? There's 2 factors that are important to look at in this reaction. The first is that the aldehyde is a much better electrophile than the ketone, so that's probably going to be the species that will react as electrophile. The second is that since this reaction is fully at equilibrium, whatever ring we form which is most stable will be the one that we get the most of. 5- and 6-membered rings are best. Smaller rings can be observed, but they're quite uncommon. So if we look at our products, we can say the first reaction requires the use of the ketone as the electrophile, so it will be fairly slow, and we form an unstable 4-membered ring as the product, so this will be thermodynamically and kinetically unfavored. The second product forms an unstable ring, meaning it too is thermodynamically unfavored. It will form faster than the first ring because the aldehyde is being used as the electrophile here. Our last reaction will be the major product because it has the best combination of all of our factors. We're forming the most stable six-membered ring, and we are using the best electrophile, the aldehyde, as the electrophile in this process. Let's try to put this all together. Propose a way to prepare each of the molecules I'm about to show you by Aldol reactions. Here are the reactions you can make. Some of these are additions, some of these are condensations. Go through one by one and propose a way to make each. Pause the video, come back to check your work when you're finished. In the case of the first compound, we can do a little retrosynthetic analysis by disconnecting these two double bonds to derive the nucleophile and electrophile we would need for this reaction. Since the carbonyl group is part of the 3-carbon chain in the center, we propose acetone as a nucleophile. Since the electrophile that we're using here has no alpha protons, these can be successfully combined in a crossed Aldol condensation. So in this case, we would only need a catalytic amount of acid, and we would not need to worry about quantitatively forming an enolate. In the second reaction, we can recognize this as the product of an aldol addition rather than a condensation. Here we have this highly sterically hindered ketone as nucleophile and formaldehyde as electrophile. Since the ketone here would be a terrible electrophile and the aldehyde cannot be a nucleophile, this also can be performed successfully through crossed aldol addition. We would only need add a base without heat to isolate the addition product. In the case of this reaction, this is a cyclic compound, which means we need to do an internal disconnection. Working backwards, we would get this acyclic diketone as the starting material for this reaction. Since this is a condensation, we could treat this with sodium hydroxide and heat it to favor elimination to form the unsaturated derivative. Finally, the last compound is an aldol addition. In this case, since the nucleophile is a ketone and the electrophile is a ketone, and there's no significant steric differences between them, we would need to quantitatively form an enolate to get this reaction to work as we've prescribed. So step 1, we would add LDA to quantitatively form the cyclohexanone enolate. Step 2, we would slowly add acetone as the electrophile. Step 3, we would add water or a proton in order to work this up and get the alcohol as the product. Next, we're going to discuss the Claisen, which is a very similar reaction that takes place with esters.